So here we go. The first type of center of mass problem, and probably the one you're going to see most often, is them putting together multiple objects. Now, if you're like, okay, Ms. Slimer, center of mass hasn't really made that much of an impact on my physics career so far, you're probably right. But here's the dealio. Okay? Center of mass is going to become more important when we get to electricity and magnetism. And the techniques we use for center of mass are going to be something we use for charge distribution, magnetic field distribution, electric field distribution. So the things we go over today, both the straightforward question, a slightly more difficult question, and the integration, are all things that you could see on this times test, but also are going to help us build some blocks for when we have to see all of this in much more detail in electricity. So the first way we can do a center of mass problem is then modeling multiple objects into one system. And I want to know the center of mass of this ABC system. So I'm going to say that I'm going to pick a different marker. I'm going to say that A has a mass of 4 kilograms, B has a mass of 6 kilograms, and C has a mass of 8 kilograms. Now, in this case, I have things in 2 dimensions because A, B, and C have separation both horizontally and vertically. So that means I'm going to have to calculate center of mass twice because I can only do it in 1 dimension at a time. Just like all of our kinematic equations, I can only do those 1 dimension at a time. Vectors, I can only add and subtract 1 dimension at a time. Same thing goes for these. So I'm going to start with the x direction. So xcm is equal to, I'm going to start with B. Now, the first thing I have to do is I have to make a reference point. I have to decide where I'm going. Okay, a lot of you guys in your little experiment just now chose to make the pivot point your 0, which is fine. But if you try this example, right, you can't just see the center of mass. I can kind of guess where it is, but I'm not going to know exactly until I calculate it. So instead, I just pick an end and start there. So I'm going to say that right here is 0. Right in the middle of B, that's going to be 0 meters. So starting with B, it has a mass of 6 kilograms. What's its location horizontally? What's its position with the reference point 0 meters being at B? 0, right? So 0. The first thing I watch students do, why get these really easy questions wrong? The first thing I watch students do is say, well, since that's 0, I'm not going to write it. I'm not going to put it on. They're like, nah, that seems lame. And then what happens is they forget to put it in the total mass because it wasn't on the top, and then the whole thing's wrong. Don't do that. What about A? How far away is A? It has a mass of 4 kilograms. How far away is it? 1 meter. And then C has a mass of 8 kilograms. How far away is it? 2 meters. Then my total mass is 6 plus 4 plus 8. So I get, that's 20 divided by 18. We don't leave fractions. Don't put fractions as an answer. That's silly. We are 2 things as scientists. First, we find information. Experimentally, we test things, we theorize, we find information. Second thing we do is communicate it. The general population, not so happy with the fractions. That's why I dress up as a fraction for Halloween every year. Okay? It's scary. It's really scary. People get scared. You can pop out at them. They're like, oh my gosh, am I baking something? No. All right. We don't use fractions to communicate answers because most of the world isn't necessarily as fluent. So 20 divided by 18 with calculator is, somebody. 1.1 what? Just 1.1? We'll just round it then. 1.1. Cool. All right, let's do the same thing in the y direction. So ycm is equal to, B is located at 0. A is located where? It has a mass of 4. Where is it located? 2. And C is 8 kilograms. Where is it located? 0. So 6 plus 4 plus 8. This is 8 divided by 18. what does that work out to be? 0.44 something? 0.44 meters. So based on that, if I draw it on my coordinate system, 1.1 is here, 0.44. My center of mass is kind of here-ish. What if I made all three masses the exact same? Where would the center of mass have been? In the center of the triangle, right? Questions about doing this calculation. For a system of multiple objects, maybe they go up to 4 objects, but really this is as hard as it gets. Questions about this one? Okay. So if they can't make this difficult, how can they make a center of mass question difficult? Because if you think that they can't, you are wrong. Let's try. I get my notebook so that I have the exact example and I don't say it wrong. Drag. All right. 2 objects with the same density but A has length L and B has length 2L. If fused together long ways, I'll draw a picture so you can see there's a picture with this question. Long ways, where is the center of mass for the new guy? So I have object A with length L, and I have object B with length 2L. Ooh, 2L. And I'm going to fuse these guys together. L, 2L, A, and B. And I want to know where the center of mass of this new, longer object is. Okay? So I'm going to work this problem. First thing I'm going to do, hello?
I'm from Mr. D's class.
Yeah.
Calculators.
Mr. whose class?
Mr. D.
Don Napati. Oh, yeah, Don Napati. I do have his calculators. However, they're spread out throughout the entire classroom right now. Can somebody hand her 9 calculators? 9 calculators. First 9 to get to there win. You get a prize. I will find candy. Only 9. Don't take more than 9. Okay, stop killing her. I'll give you all candy. Go sit down. Go sit down. There's a bucket. Where's that bucket? Oh, I have this bucket. Here. Okay, here's the bucket. Okay. All right, sit down. Let's do this. So to answer the question, I'm going to model this. I'm going to model this example as 2 particles. I don't need to model it as one long thing that's scary. I'm going to model it as 2 objects. So I'm going to model it as an object located at the center of mass of A and as an object located at the center of mass of B. So if I call this 0 meters, that's going to be my reference point. Where is the center of mass of object A? Where is it located? From 0, where's the center of mass of object A? 1/2 L, right? It's halfway in between, just like our stick from the demo, right? It's a uniformly dense object, so its center of mass is directly in the center. So this would be at 1/2 L. That's halfway from the start of object A to the end of object A. Where is the center of mass of object B in reference to my 0 meter mark here? What do we think? 2L, right? It's gone a full L to get to A. We don't care about that. That was a full L away. Now looking at B, right, it's split right down the middle. So this would be an L, and that would be an L. So it's at 2L away from 0. So we have X1 is 1/2 L. That's for A, so we'll maybe say A. And XB is at 2L. So we have the positions. Sweet. Now we need masses. All right? Let's see if we can do this. Now, the good news is, based on our equation, I know I'm going to divide out mass. So I don't actually need to know what it is. I just need to make them use the same variable. So what I need to do is I need to write mass A in terms of mass B. Here's how I'm going to do that. We know that the density of these objects are the same. So mass A has a density of MA over its length, L. Object B has the same density, mass of B over its length, 2L. Those are equivalent densities. Now, if you're like, whoa, wait a second. Density is a P. It's actually a rho. It's a weird P. Ms. Leimer, what are you doing? Also, it's over volume and not length. What are you doing? This is line density. So it is not your normal, right, volume density, which would be mass over volume. So kilograms per meter cubed. This is line density, which is why it has a different variable. It's a lambda, right? So this is saying it's just the density of this long line. We can use this anytime we're modeling an object as being just a long object. So its volume, its width, is really small compared to its length. So we can just pretend it's just a long object with no real width at all, because its length is being modeled as way longer than its width. Okay, but this would be line density. It's a similar concept to a volume density, which is rho, right? This letter. But we're only basing it off length. Another way to think of it is that these two objects have the same width and height, so the only difference between them is their lengths. So we just cancel the rest of it out. The densities are the same. So MA over L is equal to MB over 2L. So I want to write one of these masses in terms of the other. That way I don't have two different variables in my equation, and then it gets yucky. I just have one, and it'll cancel out. So what do you want to do? Do you want to write A in terms of B or B in terms of A? A in terms of B. All right, so I'm going to write A in terms of B. So I'm going to multiply both sides by L. So MA is equal to MBL over 2L. The L's cancel out, so mass A is equal to MB over 2. That's the hard part. That was the tricky part. The rest of this is just a simple center of mass equation. This was the difficult bit, finding those masses. They didn't give you a lot of information. They will give you density, and you can figure it out from there. So what I now know, after doing this work, is that MA is equal to MB over 2, and MB is equal to MB. Shocker. All right, let's solve a center of mass problem. Same equation. So MA, which is MB over 2, times 1/2 L, plus MB times its location, all over the total mass, MB over 2 plus MB. This one works out. I have MB divided by 2 times 1/2, so that's how many? 1/4. It's a quarter. 1/4 MBL. Plus, how many is this over here? Just 2. 2 MBL. So on top, how many do I have? 9/4, or 2 1/4. So I could, if I don't like fractions, write it out 2.25. Don't be afraid. Don't think fractions are the only solution. Decimals exist. They're good too. 2.25 MBL over, on the bottom I have a half plus a whole. So I get how many? 1.5. Look at that. MB. So those cancel out, and I just need to divide 2.25 into 1.5. And I get something. I don't have a calculator up here. What do I get? 1.5. That's true. So the center of mass is located at 1.5 L. which is right about here. Makes sense, right? It's actually halfway in. Questions about this? You'll see another example like it, but just keep an eye on it and make sure you understand it. Questions? All right, let's get to the calculus. Oh, yes, it's always there. Lurking in the corners. This worked because it had a uniform density, and the densities were the same. And I was able to find the center of mass as being in the middle of those objects because they had a uniform density, but what if they don't? A great example for this is a very poorly drawn bat. That's worse than first period. That was really bad. Okay, but if we're ignoring width, then this guy's density changes in the line, right? Because it has less mass at this end of the bat and more mass at this end of the bat. So it has a linear line density that changes, right? If I consider it as having width, I don't know if all bats have the same density throughout. I would assume that there's something extra in this bit, but I wouldn't know how a bat's made, so I'm not going to say anything about it. But if we consider just the line density, the density of this object changes. It's more dense here than it is over here because it's wider. And so therefore, line density-wise, this has more density than this side. So this is an example of something that does not have a uniform density. Its center of mass is not located at the halfway point. It's probably located somewhere over here. If we want to find it, here's what we got to do. There are two more center of mass equations on the equation sheet. There's not just the one, even though it looks like it. The next two are center of mass equations too. The next one says RCM is equal to the integral of R dm over the integral dm. Woohoo! That's one. The other one that we're not going to use very often, but does exist, is this guy, mass. It's written exactly like that. You'll notice this is line density. You may have to differentiate it to find it, but they rarely do this, so we'll talk about this another day. Most of the time, they're going to say, here is the density, and now you have an equation to use. So this one's probably the least used of, honestly, all the equations on the whole chart, because they very rarely ask us to do this, and we'll get to that another day. We're going to save just a little bit of calculus for another day. Right now, we're just going to handle this bad guy right here. Don't be afraid of R. What does R stand for? Position. It just means the position could be in the X or Y or both. It's just standing for radius. It's just position. So it's basically the same as X. It's just when I integrate it, I can go, instead of just being in the X direction or Y direction, I can integrate to some center of mass at a radius away. We're going to stick with just the X direction for today. So that makes that equation, XCM is equal to the integral of X dm over the integral dm. That's it. That's what it is. All right? Now, this is two integrals. Oh my gosh, I'm freaking out. Let's tackle the bottom one first. The bottom integral, right, is just going to be mass, right? If I think about this guy, right, if I just integrate it, it's the integral of a constant because there's nothing here with reference to mass. So this really oftentimes is actually written like this, with that being the total mass. This right here being total mass. There are occasions they don't give you total mass either. Ooh, that's rude. And you will actually have to do that integral to find total mass. If they don't give it to you, you might have to do it. For today's example, we're going to keep it real nice and simple, and we're just going to say that the total mass was 1 kilogram, okay? We're just going to move, not today. Today, we're not going to do that. But you might have to integrate both the top and bottom. This would be an integral in relation to mass. I will show you how to do that as well in just a second. But on a good day, it just integrates to be 1 over m. And so then my final product would be 1 over m times this integral, which is the one I actually care about. So let's do this guy. So let's say my example is that a object of length L, I'm going to use big L this time, woo, has a linear density of 6 minus 2x and a mass of 1 kilogram. Yes.
I think
What did I put wrong?
it's supposed to be an object instead of a object. Like in the first
Oh,
sentence.
yeah, okay. Sure, whatever. When I'm typing, I go back and fix it, but when I'm writing, I probably don't. All right, an object of length L has a linear density of 6 minus 2x and a mass of 1 kilogram. I want to find the center of mass. So I'm cheating just a little bit today so that we don't have to blow our brains with the calculus just today, okay? For just this question, I'm saying that the mass is 1 kilogram. So when I write out this equation, xcm is just equal to this here. Because 1 over mass, 1 divided by 1, it goes away. So that's a cheat. I'm waving my magic hands. This one practice problem, I'm saying that I don't have to do this integral. I can skip that part, and I'll just call it 1 over m, which is 1 kilogram. Sweet, awesome, moving on. So let's talk about this. It's an integral with the variable x, but I don't want to integrate it with respect to m. I don't want to do that. I'm looking for a position, so I need to integrate this with respect to position x, not mass. I'm not finding a mass. So integrating with respect to m, bad. That's where linear density comes in. They told us our density is equal to 6 minus 2x, but density is also, it's what this equation here is saying. It's just saying it in a really ugly way. Density is also a tiny change in mass over a tiny change in length. In our case, we're using for length x. So x. So if I want to get rid of this dm, I just need to replace dm with something it's equal to, right? So if I multiply both sides by dx, dm is equal to lambda dx. This is something we will do a lot. Take a density, manipulate it, so that I can replace what I'm integrating with something I actually want to integrate with. I don't want to integrate with respect to mass. No, doesn't seem fun. I want to integrate with respect to x, and now I can because density was the key. It switched it so that I can do what I want to do. So now, xcm is equal to x times density dx. Yay, now it's easy. You know how to do this. You've integrated a power function before. The rest of this is not exciting. So, density is 6 minus 2x. So all we're going to do is take the integral of 6x minus 2x squared. That's not hard. We can do that under sleep, right? We did this. We went from acceleration to velocity to position. We know how to integrate that. It's just a power function. No scary. No scary. The one thing we are going to do, which is why I'm not adding an extra integral today, is we're going to do our first finite integration. So we're not going to integrate just over a big, massive, infinite integration. It could be anything. And have to add that plus c at the end. We're going to integrate over some very specific limits. The length of this object. Because the center of mass can't be everywhere. It can't be all the way over there, 4 L's away. It can't be over there, 18 million L's away. It can only be somewhere between 0 and L. So I'm going to integrate from 0 to L. That's what I'm going to do. It's not scary, don't worry. It's all gonna be fine. So first thing you do, take an integral. Somebody tell me what the integral of this is. I'm gonna put 0 and L right here on this line to remember them. That's literally why they're there. I haven't done anything with them yet, so I can't just get rid of them. Can't get rid of them because I haven't used them yet.
Where does 0 and L come from?
They're the limits of integration. So my center of mass, right, this is some rod of length L. And I'm trying to figure out where its center of mass is. It's limited to being between 0, one end, and length L, the other end. It can't be way over here, and it can't be way over here. It has to be somewhere on this rod. So that's a limit to my integration. It can't just be wherever I want it to be. It has to be somewhere on here. So I'm integrating from 0 to L. Watch what I do when I do that. It's very simple. But what's the actual integral of 6x minus 2x squared? What does that turn into? Minus 2/3 x cubed. Woo! Very difficult stuff. Okay. I've done the integration. It was the hardest part, I'm sure. Right? When you have limits of integration, here's all you have to do. You do final minus initial. So I plug in L first, and then I subtract, plugging in 0. This is what I do when I have limits of integration. I integrate, and then I actually calculate, because I had a final minus initial, because I have 2 limits of integration. Can't be outside those limits, has to be somewhere inside. Nice and easy, this is 0, that's 0, so my answer is 3L squared minus 2/3 L cubed. Again, waving your magic hand and saying that the mass was 1 kilogram. Magic wavy hand. Sometimes it is, sometimes it isn't. That's a lot of it. I have put all of the calculus in this unit this week. There are really only 2 things, this and drag force, which is what we're going to do next class. I've done that on purpose for those of us who are new to it, the calculus that we have to get into this unit. A little scarier, yeah?
Sorry, we're here to wash pans.
Yeah, go back there. It's a little scarier. It's a little more difficult than what we did last time with just the basic integration. It's there. That was the integration we did. Just had to do a little more math around it, right? So I'm giving it to us at the very front end so we can practice, 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 practice. Okay? All right. With the remaining part of class, I'm turning this